Great. So BIP-85 is something that, thank you for inviting me to speak, by the way. I think we're aligned in terms of enabling individuals greater sovereignty and greater control over their cryptographic secrets. And I think we all understand that this is the primary barrier to adoption. So it's good that we have the wallet vendors listening at some level. And I originally got into BIP-85 to solve some of my own problems, namely that creating multi-sig Quora becomes like a big project and it's very expensive to change out your seed sets. And I mean expensive in terms of time. And the real promise behind BIP-85 here, before I move forward, I just want to say my contact information is here. And I've got an open source repository that you can look at all the tools, which I'll be demoing today in this talk. And let's see. Okay, great. So I think you all understand, or let me state that the primary purpose of BIP-85 is essentially to use a single secret as the root of a tree of secrets. And this means that you can derive millions of secrets from a single seed. This is all based implicitly. It's a slight generalization of BIP-32, which I'm going to get into, and I'll show you how this works in just a moment. But that's the key idea. And a very quick refresher here: the derivation paths from BIP-44, we're going to use a generalization of those. So M there, that is your master node. And then you have these series of slashes. This is the path that you're looking at here is 5 levels deep. And this single apostrophe indicates hardened derivation. We'll talk more about that in a second. And every segment in this path is an unsigned integer. So it's a 32-bit integer. However, the leading bit is used to indicate hardening or lack thereof. So if you have a leading 1, that's a hardened child. We'll talk more about what this means in a second. And if you have a leading 0, that's an unhardened child. So quick refresher on BIP-32, because this is kind of the core of how BIP-85 works here, is that when BIP-32 was conceived, it's funny because a lot of the terminology for this actually gets quite sloppy, but we have this progression from master seed to master node. And we're going to go through all this derivation as it relates to BIP-85 in just a moment, to accounts and chains and addresses. And the thing that hierarchical wallets were designed to do is you may want to have watch only wallets. You may want to have a complex multi-tiered business where some people have the permission to see the transactions, but not the ability to sign the transactions. And so this is this world that the HDWs, hierarchical deterministic wallets in BIP-32 really open for us. And pretty much today, every wallet vendor, whether it's a cold wallet or a hot wallet, supports BIP-32. I want to go into detail here because my goal is to make it so that you will be able to use and implement the pieces of BIP-85 that are generally useful for secrets management. And in this presentation, that's really the context in which I'd like you to think about BIP-85. It is a generalized keychain and it's built on top of HDWs. And the cool thing is, pretty much all the software out there already has the algorithms and already has the implementation to do this. So there's just some small tweaks required to generalize the BIP-32 chain. I think everybody understands the irreversibility of hierarchical deterministic wallets. They're irreversible up to hardening. I won't get too deep into this, but I'll talk a little bit more about it. And the reproducibility, of course, is key. And what it means essentially is that if you have the master node, or if you have the root circuit or the precursor to the master node, I think they call it the master seed, you can, and a derivation path, you can reproduce as many secrets in the tree as you need to. And so this is a pure function essentially. And as long as you have the seed and the derivation path, you can go anywhere in the tree. And it's fairly easy using the child index to jump to create a fresh secret, which I'll explain in a moment. Some of these asterisk slides I won't really go into. I do think it's important to understand the yin and the yang of hardening. And so unhardened keys are useful in that you can look forward. So when you have a watch only wallet, you use an extended public key. And that allows you to see what all the child addresses are. So there is an advantage to having keys that are unhardened, but that also makes them more dangerous. And so a compromised XPub is a loss of privacy. A compromised extended private key is compromised funds. And then this strange property, what unhardened children, the undesirable property that they have is if you have an unhardened child key, private child key, and then you have the XPub of the parent, you can actually get the extended private key of the parent. So this is where the care comes in. And actually, the consequence of this is that in BIP-85, we generally use all hardened keys in the derivation. The order is quite important and the terminology is important. So the mnemonics from BIP-39, those are the seed word phrases that everybody's familiar with, those get normalized and run through PBKDF2, which is essentially a multi-round HMAC. And I think there's a fixed number of rounds. It's all in the spec. I think it's like 2048 rounds. This is usually the most computationally expensive step in key derivation. You'll see that it dominates most of your CPU time because it is an iterative HMAC. And you keep HMACing until you hit the number of iterations. The extended private key is then one more HMAC. There's a special process for deriving, according to BIP-32, the root key. And then at each level of the derivation, there are some pretty simple elliptic curve operations and another HMAC that governs the generation of the secret. These I won't get into. This is kind of specifics of BIP-32, but it's here for your reference. I want to talk a little bit about some of the software that has been written so that you can actually experiment with BIP-85. And I think, to Shannon's point, this is software for developers who are writing applications. And this software, well, I did write it for myself so that I could generate seeds offline and multi-sig Quora and these types of things. But it's really for developers to experiment with as a command line tool. There are also Python libraries, and I want to show you a little bit how that works by way of getting to what are some of the things that wallets should be doing with BIP-85. So it's fairly standard. You can generate mnemonics in any language. You can pre-print mnemonics. This is the first command here. And this either uses user-provided entropy that you can provide as an integer, or it will use the Python secrets library, which should be cryptographically strong source of randomness. The next piece is validation. This is going to become significant because I'm going to talk about seed steganography and the ability to generate seeds from non-traditional sources like decks of cards in just a second. But Validate's job is essentially to check if the words are in dictionary. And then, of course, BIP-39 has the checksum, which is part of it. So it also checks that all the words are in dictionary, and it checks the checksum. And I guess one of the things that I'm experimenting with in the open source is this concept of a free language, which will let you input literally any string. And this is the beautiful thing about PBKDF2. It does not care what you input. So this is kind of the basic idea. How many people have heard of brain wallets? Yeah, so no, I'm not saying they're secure because, as I'm saying on the slide, more entropy is better, but PBKDF2 is input agnostic. So if you had a phrase that you had memorized and you ran it through PBKDF2, and this phrase was of sufficient length and sufficient randomness, then in theory, you have the ability to derive a seed from anything. And this level of portability is really important. War zones being an example. One of the problems that seed words have is that if anybody finds those, they're instantly recognizable and they can instantly guess, okay, this must be part of a Bitcoin seed. So steganography is the idea that you can hide the existence of this secret or the precursor to the secret. I do have they haven't gone anywhere on the BIP proposal stage yet, but I do have some early proposals that I'm linking to here for how to do a few of these things here. So we talked about mnemonic, we talked about validate. The XPRV is exactly what you would think, is that once you have a validated string, you can then turn that into an extended private key. And this becomes our master node, as we showed in the BIP-32 diagram. And now is where things get interesting. So the fourth command, and these are designed so that you can all chain them together, and they really just reflect the order of maturity in that BIP-32 diagram, or the order of derivation. So once you have an extended private key that can be treated as a root, you can now call derive. And derive is really the application of BIP-85. And all you're doing in derive, you need really only a couple of parameters for derive. So you need the root secret, you need the derivation path, and BIP-85 tells you how to produce this derivation path. And I'll show you a little bit about that in a second. And then you need an application. Okay, so mnemonic in this case is the application. And this is kind of the inception or bootstrapping moment, because we've taken one mnemonic and turned it into another mnemonic. And you might think that this is totally stupid, but you can turn this into millions of mnemonics. So from your root seed, and you can imagine developing a multi-sig quorum this way, from your root seed, you can now develop zillions of mnemonics and populate as many hardware wallets as you want. And it's much easier than having to independently generate those secrets. And the security and irreversibility of that is really contingent on ECDSA and the BIP-32 hierarchical deterministic wallet tree. Let me just pause there and see if there are any questions. If I'm going too fast or too slow, there are a few more things I want to get to, but I just want to see if there are any questions from the audience. Okay, great. So I don't know which algorithm they used in the Matrix movies to generate what you saw on screen, but they should have used BIP-85. And one of the neat things you'll see here upper right, that there's a discrete random number generator in BIP-85. And this means from a single root secret, you can actually produce arbitrarily much cryptographically strong entropy as you desire. And in the BIP-85 spec, you can use this. How many people are familiar with RSA key generation? So when you generate an RSA key, you have the option of providing a source of randomness to the RSA algorithms, and they don't know ahead of time how much randomness they're going to consume. So a discrete random number generator lets you can hand it off as a first class function, and then you can just pull as much random because it's essentially a scheduled repeatable, given a fixed seed and given a fixed child index, stream of entropy. And so again, the point is here is that RSA is throwing entropy out and consuming entropy, and again, you don't, depending on what you get, you don't know how many bytes of entropy you're going to need. So this application allows you to just pull from a random and repeatable stream of cryptographic entropy. In the near future, I will be the maintainer of BIP-85. So the original author is by the name of Ethan, and he's not been reachable for a couple of years now. And so I've started to add new applications, and these are in pull request. One of the things that's missing from BIP-85 is the ability to generate pins. So you might want an ATM pin, you might want a hardware wallet pin, and none of the existing password schemes suit that. So the dice application, you can see, and I'll show you the derivation paths for this in just a moment. The dice application lets you say, I want -n 100 die rolls, and I want 6-sided dies, and then it will do the rolls for you. For a standard pin, you would obviously use a 10-sided die, and you can get as many rolls as you want. And this is actually built on top of the discrete random number generator that's part of BIP-85. So there are a few other password schemes here. So again, what is happening here? So I want you to notice here that the application is base 85. And I'm going to show you how these are generated in just a second. The application is base 85, and this allows you to generate a password. And if you change the -I, the child index, you completely change the password. So you have 2 to the 31st of these child indexes, I guess child indices, hardened ones. And every time you change the child index, you get a completely new secret, because that's how HTWs work, right? And that is why, for instance, in a standard BIP32 wallet, a standard Bitcoin wallet today, the addresses are all orthogonal to one another and completely independent set of secrets and signatures. I want to talk a little bit about what we've done from an implementation standpoint, from going from BIP32 to BIP-85. So we already have in the BIP32 HDW tree, we already have the 512 bits or 64 bytes. And by convention, the first 32 bytes are used as the secret for ECDSA, and the second 32 bytes are used as what is called the chain codes. And what Ethan did in developing this spec was say, hey, what we have is 64 bits of cryptographically strong, irreversible entropy. There's no reason that this should be just confined to ECDSA or elliptic curve cryptography. And so that's really what we're doing in BIP-85. The derivation paths you can see here, they're all documented in the spec. This 83696968 apostrophe is the purpose code specifically for BIP-85. And then you have a series essentially of arguments that your application takes. For instance, what language are we talking about? How many words do we need? 12, 15, 18, 21, 24. And then what is the index? Again, you change that index, you get a completely new secret. So who cares? What does this offer to our users? Simplified operational security. I personally find this much, much easier than, first of all, what a nightmare rolling dice is. Like, it's really hard to trust. I mean, you really shouldn't trust other people's sources of entropy. So this is a much simpler in terms of you can produce dice from your own secure secret that you've created. The possibilities for steganography are really neat. This has, it turns out that a deck of cards has the same strength as about 21 seed words. I think it's like 221 bits of entropy, something like that. And this is much easier than sitting there and rolling dice. There's a bunch of weird methods for generating seeds, but it does have a trade-off, and the trade-off is that this does not implement a checksum. And my point is here, you can use these as inputs to BIP-C, or you can use these as inputs to PBKDF2, and now you have your secrets. And there are all kinds of neat things that I go through in the spec. You can store secrets in chess games, you can store them in files, and this is much better for people who are leaving war zones and don't want detectable secrets with them. And it could just be something on your hard drive and nobody even has to know. Again, there are plenty of trade-offs. I'm not saying this is strictly better or dominates the existing paradigm of BIP-39 seed words, but there's a much bigger universe out there. And the most important thing for this group, I'm going to try and wrap up here, is really that hardware wallets now have everyday use cases for superior password management. And I've done a little comparison here between what you could do with BIP-85 and what you could do with Apple Keychain. And I think the trade-offs heavily favor some kind of BIP-85 style keychain, cold versus hot roots. You don't have to back up the ciphertext at all. As long as you have a seed backup, you just need the derivation path. And if somebody finds that derivation path on your machine, it means absolutely nothing to them. It does not give them access to the secret at all. Up to hardware security and up to the air gap of your wallet, no third party is required. Cold Card actually has the BIP-85 support is not good, not great in the ecosystem. I hope that changes. It's not difficult to do. But Cold Card actually has this ability to, you give it a child index and it'll give you a base 85 or base 64. I don't remember which of those two they do. Maybe they do both. Password. And there's all kinds of neat things you can think of. You can have derived keys that are derived just in time. So the secret doesn't necessarily have to be a hot secret. And you can submit like, hey, I'm ready to log into this service. And okay, let me plug in my hardware wallet. And assuming the implementation is correct, the secret remains cold and offline, and you just get a just-in-time secret. And because you can have millions of these, you can do secret rotation. I mean, there's all kinds of neat things. So let me just see. There's a message in the chat here. Okay, Foundation Passport has BIP-85 support too. Nice, nice. And my goal really is to get as many hardware wallets as possible to support BIP-85. We can talk more about that. So very, very briefly, there are a few limitations of BIP-85 that I'm working on, correcting some of the test vectors, updating the languages. The application code process is very arbitrary and it's not very user friendly. And anybody who's had to back up a multi-sig wallet knows like, oh, I have to store this derivation path too. What are these slashes? So there's a lot of work that needs to be done there. As far as ECDSA, I'm just making the point that if ECDSA ever gets broken, this all falls apart, but so does the entire Bitcoin security model. So two future notes, and then I'll wrap and see if there's any questions. One of the things I'm working on and proposing in this pre-BIP is that so this path that we talked about, these derivation paths are just integers. I can't read that and be like, oh, this is the password this is my Google password. This is my Apple password. So what I think we should do is we should use JSON LD and we should hash that into an integer. And now we have these repeatable semantic chains. So you could imagine that a desktop wallet would just store this tree of JSON objects. It doesn't have to store the secrets at all. And you can have a key service that provides the secrets just in time. I think this is a superior model. I think this would lead people, if we make it easy enough, I think this could lead people to use their hardware wallets every single day and not just once a year for some Bitcoin transactions. So I think this is huge potential value. There's a lot of usability R&D that needs to be done, but I think it's huge potential value for the hardware vendors. And then I do have this little pre-BIP on these what I call free mnemonics, and I talk more about what the trade-offs are. In short, it's much easier to hide these steganographic secrets, but they're easier to get wrong because the user has to implement their own checksum, or the protocol needs to have its own checksum. But I think those trade-offs are really worth it. Again, given the portability of something like this, which is very easy to repudiate, I can just stick it in my pocket and leave the country or leave the house. So I quite sure I went quickly, but I hope that was stimulating for you and that you were able to think about BIP-85 as a mechanism for hardware wallets to provide more value and a generalized keychain. And if I don't, I'll let Christopher run the agenda, but if there are any questions, I'd be happy to answer those.
Yeah. So thank you very much. I appreciate the detail. And we can also open to other questions, but I very specifically wanted to talk about some relationship with the blockchain commons, Gordian standards, and where things are going, et cetera, and BIP-85. So first off, I'll say the reason why I did not initially support BIP-85 was that it wasn't clear to me cryptographically that the reproducing the whole master seed capability of it and such was actually added that much security to it. It felt like a bit of overkill as compared to just doing PBDKF on a secret. They're both cryptographically just as strong. So in this, so that, I had some reservations about that. But I will concede that, as you said, a lot of people have implemented it already because they're already supporting BIP-32, BIP-39, et cetera. And it's well understood. And it's a little bit of the problem that happened with SSKR versus SLIP-39. SLIP-39, a lot of the people who developed uh, BIP-32 and BIP-30, not later, BIP-39 are not completely happy with their choices in retrospect, if you talk about them as a postmortem. And the Trezor people basically said, oh, we've been working with Blockchain Commons and others on this secret sharing technique, but we're just going to, back away from the way the master key is generated and do it the way we think it always should have been done. So it does it in a completely different way, which means that master keys that you create with SLIP-39 are not compatible with the master keys that you create with BIP-39. And we felt that was really broken and caused lots of user problems and segmentation, et cetera. So we decided to not support SLIP-39 and develop SSKR. And there have been a number of people who have come back to us and say, oh, that's kind of hidden in there that SLIP-39 does this derivation at the end when you actually implement it differently. And we're going to talk a little bit about that in a little bit when we talk about the ledger seed tool. But my point back to BIP-85 is, they're doing it the same way consistently or whatever has some advantages. So I think that's my first point. The I do want to hopefully keep separate some of the as you say, free mnemonics and such. It turns out that a lot of wallets don't implement that fully or completely, or only work with English words and things of that nature. So there's some interesting complexities there. Also, I mean, I will point out that, this was an old project. When did this is 8 years ago. So this is basically how to turn a binary object into a poem to make it memorable. I did a lot of study about what makes things
Mm.
memorable and how. And actually, we have also in in the same repo a little Python app that converts things into memorable poetry. And I was able to derive there, for instance, all of these, how do you do iambic is obvious there, but also some of these word lists are things that are deliberately, it turns out for memorization, there are two properties. One is its valence, which is its emotional connection, and the other one is its concreteness. So if we think about a table, it's very concrete, so it's easy to keep a picture of a table in our head. Truth is not concrete, but it has a lot of emotional connection to it. So it has high valence. So you want to have words that have both high valence and high concreteness to make it memorable. And so that was what this original research was. This later ended up going into informing the work that Wolf and I did on byte words, which we needed for another reason. We needed byte words because of a problem with QRs and how they encode things. And we needed to be more optimum than things like base64, which breaks QRs. So, or makes them double the size. So Wolf did a lot of work to basically apply all of these things into a word set that was a little bit different, all 4 letters, all high valence or high concreteness, and but also did some unique things. The Demerol-Levenstein distance was high, and things like the first three letters are unique, the last three letters are unique, and so is the first and last letter, and no homophones, etc. So I think my point is that between the problems of how different apps support BIP-39, I don't want to say improperly, but I would say the majority use like an English table and construct it and don't do it the original way, which means they won't work with, Japanese list and such, is problem one. And then there's this larger problem of, how do you create these word sets? How do you make them good, et cetera? I would love to talk with you more about that and support I like your CLI approach of, having an arbitrary text and being able to turn that into a dictionary. But I think it should be kept separate from BIP-85. I think it shouldn't be part of BIP-85.
You totally
Uh,
agree. Sorry, go ahead.
okay, no, no, continue.
That was a beautiful summary. I think you nailed all the high issues. And just to reiterate, this getting free mnemonic and steganographic mnemonics is totally orthogonal to BIP-85. I do want to talk about SSKR very quickly, just to say that there's no requirement on how you construct the root secret for BIP-85. So you could have Shamir secret shares that are used to construct the root secret for BIP-85. And yes, those are all indeed separate issues. And I think the main trade-off, to your point, Christopher, the thing I like about BIP-85 and why I would recommend it over what happened with Slip 39 is the vendors already have the implementation. I think it's just a matter of nudging them to use that.
Yeah.
I'd like
I
to
also wanted to
make a
point
quick
out one
point
of the
to
other big
Christopher.
values in BIP-85 is, so we did this book in 2019 after a couple of years of talking with Bitcoin Core engineers and big holders, et cetera, who collectively lost millions of dollars, now probably tens or hundreds of millions of dollars, because of loss of keys. In particular, things like using BIP-38 encrypted keys, which still is a bugaboo that we haven't got a good answer for, because of the similar problem that you're running into, which is there's no checksum on these passwords and such, on these passphrases or IDs. And I think that was one of my other reservations about BIP-85 was we still didn't address that problem. And then we found in in 2019, 2020, and 2021 that despite we really working hard to make these as easy as possible, so you could have one really good, strong, random seed that was properly secured and backed up, et cetera, that people wouldn't even spend the 1 hour to do it. I mean, the prior thing I think was called Glacier. Yeah, it was the Glacier project. And, Glacier project, you had to buy, old hardware that doesn't, and it was like this day-long, mess. So we got it in this book down to like a 1 hour exercise to very carefully create a master key that you could create offline. And we also created a tool called LetheKit, which basically you could in a device that completely, let me do I have a picture? Lethe, yeah. Yeah, so this is LetheKit. The idea was you have a relatively dumb device that could basically take an offline seed. You could take this into the safe deposit box, put in your the seed, and then it would create the SSKRs or the other different types of things. It would be great to add BIP-85 to LetheKit. And the choice of the hardware also was it has no memory. You turn it off, it's gone, all of that kind of stuff. But obviously, nobody's made a LetheKit, cheap enough, commercially available enough. But it sort of illustrates the problem of, people don't want to spend the hour to protect that one key, and then you still have to create the child keys. I think BIP-85 offer some opportunities for some low-end hardware like this. Maybe do this on some kind of a, not so much a Java card, but maybe there's some small devices, credit card size, but thicker that could do this in some interesting ways. The way we ended up ultimately recommending was these offline QR codes. And we have a bunch of discussion in our repo about what happens with multi-sigs, how do you care for multi-sigs, et cetera. Probably the biggest one was the designing SSKR. No, wait. Trying to think, where is this is the newest one. So we talked to, one of the things that was happening with multi-sigs is that the use, even with our very, very carefully designed processes for multi-sigs, they're still too hard. There were too many steps. It was that hour of time. But it was also all of these decision points, things where a user had to make a decision or had to do a little bit of research or look something up or whatever, the actual actions that they had to do all the steps, and what could wallets facilitate. In using envelope request response, it just became 2 decision points, 6 places where you needed to confirm that the steps were done properly, only 1 research instead of 11, 14 actions rather than 31, and there are now 33 automated actions that require no human intervention. You just do the steps. So this was just taking our very rich scenario to create one really good master key, which I think is part of the problem here. No matter, even if you have BIP-85 and more people do it, you still really need one good master key, whether or not you want to put that on a passport or have it completely offline or whatever is the right scenario for you, or use it in a multi-sig scenario. There's just, some interesting things there. So I like BIP-85 in that it helps there, but I'd love to see it integrated with the kind of these larger thoughts. And I do want to reiterate, I would love to figure out in BIP-85, since there are really only 2 organizations that have deployed it in wallets, can we at least have a BIP-85 BIS or something that recommends that the secrets have some form of, I mean, it's turtles all the way down. So we've just created a secret in which we have to do special care to make the secret a good secret, whatever, and then be able to make it resilient and SSKR it and all that. Only to have a new secret that now we have to annotate, and we have to say what is the key with it and whatever. That maybe there's a BIS version that has some kind of checksum on those. I think that might be a worthy effort. So you can at least, check and see, is this a valid secret that we're using to derive the BIP-85 path?
Christopher, may I make a quick comment here?
Sure.
You showed off the bytewords spec, and one thing about the bytewords spec is you can use raw bytewords, just the correspondence between the 4-letter words and one of the 256, 8-bit values. But the actual spec, if you use it, use it in its full sense, then the sequence that you encode would be CBOR. In other words, if you just want to encode a binary string, it would start with a length byte, essentially a CBOR length byte. And then when you actually encode it into byte words, the last 4 words are a CRC32 checksum. So by adding 1 byte at the beginning or 1 word at the beginning and 4 words at the end, you would have a well-formed set of human readable words that, for example, if your seed was 16 words, 16 bytes or 32 bytes, whatever, then, you'd have that many words plus 5. And would have a checksum in that case. Of course, you don't have to go all the way to words. You could just use the byte values, but then there's this easy correspondence between human memorizable words and that actually have a checksum and the actual seed data. So that might be a way of having, adding a checksum in a fairly usable, human handleable way.
Yeah, I mean, I would love, so I would love that you take a look at seed tool, the command line tool. Let's see, where is the docs?
Yeah, another thing about the seed tool that we have, which is written in Rust, it does take, it has a deterministic function or parameter, and it does, I believe, if I remember off the top of my head, I wrote the code, uses HKDF to hash that into entropy. And the primary use of our deterministic field is for testing purposes, because we either want you to generate your own entropy using cards, dice, or whatever, as much of a pain as that is, or use the built-in cryptographically strong random number generator, depending on what you trust more. But we also offer the deterministic feature, which could actually be brought in line, I guess, with BIP-85 in certain ways. And then the other thing we don't do, which BIP-85 does, is allow you to BIP32 style provide a derivation path, if I understand correctly, so that you're essentially deriving a seed from a BIP32 like path. And so that's something that could be added to seed tool that would be BIP-85 compatible. So that's just a few ideas off the top of my head, if that makes sense.
Yeah.
Quick comment there that the checksum is the easy part. It's entry errors that are difficult to avoid. So in other words, you could take the fingerprint of the master key, you can hash the input. Here's the problem though. So let's say I have a fingerprint for this deck of cards. That doesn't make it any easier for me to get the deck right when I enter it on a keyboard, right? So there's just
Yeah,
two
the nice
two
thing
different
about byte
steps
words
there.
is it's actually very difficult to enter it wrong, because
Right. Yes.
because the first and last letters are unique, the first three letters are unique, the last three letters are unique,
Bingo.
no homophones, all those things. So yeah, so that actually is designed to reduce data entry errors. Even if you have to speak the words over a telephone for somebody to transcribe them or enter them yourself, because you can just and if you look at our iOS seed tool, when you enter byte words, you can enter very little. Actually, you can enter rather sloppily, but it will actually tell you along the way
Yeah.
whether or not you are entering valid byte words.
And that error
And of course, the
correcting
checksum has to be
property
correct
is
on top of that.
that is huge, and that's why dictionary words are so useful. And obviously there are more redundancy checks here, but that's what's hard about the steganographic seeds. Like if you have a chess game or
Yeah.
a board game, like, oh
I'm,
well.
I definitely want, I think that's great to be able to support, but I think maybe I'd love to see you support as maybe the base, as some kind of a base, byte words, or, some things of that nature would really help. And then, also you have your own, format for how you format the seeds, how you format the cards, how you format dice, the commands you use for dice, etc. I would love that, before we kind of move seed tool CLI to formal release, that maybe we talk about making those be more common, because I would really love to see. I mean,
Yep.
one of the things that I
Yep.
really loved about LethiKit was you'd use dice with LethiKit, using the deterministic mode, and always get the same thing. And then you could do dice with the CLI tool on a computer, and you could do dice using a piece of paper and a little bit of manual calculation for the CRC at the end. You do it all these different ways to at least determine that all those devices were consistent before you use them for the real thing. So there was, it's not precisely a reproducible build problem. It's a reproducible result problem. And it's, not perfect, but if all three things, when you give it the same dice, give you the same seeds, then you can use that same technique for something that on the most trusted of those places, and feel like you have some confidence that it's not doing bad things. So Again, I'd love to, work with you to have a Python version of what everything that Seed Tool CLI does, and have Seed Tool CLI support, the BIP-85 things, et cetera. And again, if we can puzzle out how to we have a separate app for bytewords. Because of this, rather than
Right, there's a
building
byteword CLI tool as well, but yeah, so we're a big advantage I see of the BIP-85 is just being able to derive seeds from seeds, as opposed to BIP-32, which is deriving keys from a seed or a root key, which we derive from a seed. So we strongly at Blockchain Commons have had a commitment to cryptographic seeds as useful for a long time, and BIP-85 does seem to fill a gap in what we're doing. So just how we kind of integrate it and how we make sure that there's maximum interoperability for the good of all our users and all that, I think is the question going forward.
Yeah.
Yep.
I
And
would
now
love to see a BC bytewords in Python, and then the reference. There's also a reference CLI app. Both those are in C. We haven't moved those to Rust, but again, I think the more consistent we are, the more things we offer.
agree. Less closing thought would be that now not just seeds but passwords, and again, I'm excited about that because users need this. And I also think we're living in an era where people are scratching their heads and be like, do I really want to trust one password like for like literally everything in my life, every account, every bank account, like, then that's a lot to ask for somebody. And then the thing that really pained me, what I'd like to do and where I'd love your help on the BIP-85 spec, is making it more developer friendly, because this whole concept of, oh, these are the arguments you take in and this is the return value, is like totally up in the air, because
Yep.
paths weren't really designed. And how are people going to build good applications if like they don't even know, there's not even really, I'm trying to work on this, a convention for ordering the arguments, they're all integers, like
Well,
it's
that was one of the ones when you were talking about that. That's exactly what DC bore and envelope do. Like you
okay.
were showing a JSON LD structure, which I have far too much experience with JSON LD, and it's I'm an invited expert on the W3C on two specs that use it, and boy, a lot of people don't get it right. It's hard to do correctly. Envelope addresses a lot of those by basically having everything be ordered deterministic. It's moving forward as an IETF standard. So like all your maps are sorted, numbers are reduced, et cetera. So I think there's some real opportunities for that structure that you kind of designed as a JSON LD thing for it just to be an envelope. And the advantage also is that if you want to share that, you can elide any of the individual elements that maybe aren't necessary for you to be able to do a restore, or maybe are too long. I mean, we've talked with one wallet developer who only can put 1,000 bytes on a storage card. But if you're doing SSKR envelope and you've got a really long description, or you have many output descriptors or many BIP-38 passwords, or all the your transaction data, that's not going to fit into into that NFC card. Well, what you do is you elide the stuff you don't need, but because it has checksum in it, I mean, it has hashes of all the things that are missing. When you get the a sufficient quorum threshold, and one of those thresholds came from something that was secured on Google or Apple, it has all the extra data that you need, and but it's that offline version of it that let you decrypt it and then be able to see and go, oh yeah, these envelopes match. There's extra data here. So again, there's some real opportunities to leverage envelope and other things to for that purpose as well.
Christopher, if I might jump in and give a pitch we're going to be releasing a comprehensive Understanding Gordian Envelope video soon, which I think everybody here should watch. It's going to basically go into all the architecture of Gordian envelope, our lay the foundation concepts, and then go through a bunch of applications and extensions for it, including our SSKR extension and what DCBOR is, and all these things in a very kind of understandable way for technical people. So I've been working very hard on that, and it's in review now. So we hope to come up with that in a few days, and it should answer a lot of your questions about what are we even talking about when we talk about Gordian envelope and deterministic CBOR and all of that, and why we think it's really going to become the go-to over things like JSON LD.
Ken, you were one of the parties who's actually implemented BIP-85 for your wallet. Do you want to share with us a little bit about, what what was involved in making that decision and your thoughts, regarding some of the things we've been talking about?
I mean, we were getting a lot of actual customer requests for it. It actually wasn't on our roadmap, but we were getting a lot of requests for BIP-85. Today, you can create 12 and 24 word mnemonic seeds as well as Noster keys. And we'll probably be extending that in the future. But I mean, it was trivial to implement, right? I mean, we already do key derivation, or sorry, derivation paths, and so I think it took us like 2 days to fully integrate it and make it work. So it's such an easy thing. It was such an easy win for us that there was like no reason not to do it.
Did you
Great.
have your own application for Noster keys, or is that?
So there was like a NIP Noster improvement proposal, I think, that had the defined derivation path for it. But I think I'm not sure it's like, I think it's a standard. It's like
Right.
a de facto standard. So we just, people were asking for it, so we implemented that as well. But I think there'll probably be other better ways of doing that in the future. I think there were some ways of doing like time box derivations as well, so that you could like have a signing key outside your hardware wallet that was valid for a certain period of time. So I think it's been a few months since I looked at any of that, but I know they were doing some they were making some changes or some proposals so that you could do signing without having to go to your hardware wallet every time if you had like the private key stored on the wallet.
Or a child of the private key.
Yeah, it was basically what they were doing was like having a child with a private key that was valid until a certain block or something like that.
So anyhow, we definitely, I'd love to have, we used to have more of the Lightning community here. I know they watch the videos, but the time zones in Asia, it's like Europe or Asia. Can't do both. But there is some interest in the Lightning and Noster and other communities in this stuff. We also have, a little bit of discussion with other blockchains, and some of their needs. I know, for instance, Ethereum really the guy who designed the first major wallet, which is what everybody kind of bases their architecture on, hated BIP-32 and BIP-39, and basically all they do is create one key. That's the only place they use it. They don't really use derivations, and that causes some interesting complexities, because that means you're using the same keys to spend money as you are to authenticate to a website, which is just not a good idea. So we have a lot of thoughts about, and some articles about key separation and key usage and things of that nature. I'd love to figure out, when we're writing either a separate BIP or some other spec on how these additional secrets are created for the paths, that would allow us to have things like a key usage, saying, hey, this is only, use this path for Noster, don't use it for other things. Or yes, this, you can be paid on this, even though it's also a Noster key. That type of usage, key usage is powerful. Anyhow, I want to make sure we get to our next presentation. Any last questions from anybody? Can also bring them up on our Signal channel. It's monitored regularly, so